Alright, so let us next see this 12th one. In this one, we first consider the set of all positive integers that which we are denoting by z plus, and we are considering three order relations on this Cartesian product of z plus with itself. The first one is our familiar dictionary order. The second one is another such similar one but different one. In this second order, the ordered pair x naught times y naught is considered to be less than x1 times y1 if either x naught minus y naught is less than x1 minus y1, or they are equal and y naught is less than y1. Okay, so you can see that the definition has similarity with the definition of dictionary order. And in the third one, in place of minus, we have plus. In this case, this ordered pair is less than this one if either the sum of the coordinates is less than the sum of the coordinates, or the sums are equal and the second coordinates are like that. Now what do we have to do? In these order relations, we have to see which elements have immediate predecessors. And we also have to answer whether each of these ordered sets has a smallest element. Plus, we have to show that there are three different order types. Okay, as ordered sets, none of them is isomorphic to any other. They are distinct different order type sets. So the first one is dictionary order. It will be a good idea to draw a figure first. And in fact, in the figure itself, we are going to see what's happening. The figure is not necessarily a part of the solution. If you want, you can make it a part of the solution. So the figure simply just goes like this. I won't even need a ruler also. You have these points, right? This is your 1 times 1, or in the old notation, if you write it as an ordered pair, 1 comma 1. Then this is 2 times 1, 3 times 1, 4 times 1, 5 times 1, and so on. Just above this row, you also have these other points, which you know what they are: 1 times 2, 2 times 2, then 3 times 2, and so on. So like that, these things are going without any end. And also, such rows continue to appear without any end. So you just have more and more rows above these rows. Okay, now what does the dictionary order say? Let us recall the definition of dictionary order. In the dictionary order, two such ordered pairs will be related like this if either x naught is less than x1 or x naught is equal to x1 and y naught is less than y1. What does it mean geometrically? Let us just take 2 points, say 1 times 1 and 1 times 2. For these 2 points, the x coordinates are equal. Both of them are 1. So how do you decide which one of them is the greater one? By looking at their y coordinates. The one having higher y coordinate by definition is the greater one. So this one has the higher y coordinate 2, here the y coordinate is 1. That means this element is greater than this element. Similarly, if you go higher than that, this element will be greater than this element. So in the dictionary order, first of all, we have this direction of things increasing. Okay, straight up. This is the direction in which you get higher and higher elements, but that is along a single vertical line if we are talking about the figure. What about points that lie on different vertical lines? For example, what can we say about, say, 1 times 1 and 2 times 2? For this type of points where they lie on different vertical lines, the x coordinates will not match. So looking at the x coordinates themselves, you will be able to say which one the greater one is, which one is the greater. We do not have to look at this y equal to 1 here and y equal to 2 here, because the x coordinate of this point is greater than the x coordinate of this point, which is 1. So this is greater than this. But actually that's also the case with this point and any point on this line, because any point on this line has x coordinate 1 and that 1 is less than 2. So although this point 2 times 2 geometrically is at a lower level than this some other higher points which lie to its left, but still by this definition this point will be greater than all these points. And that is why when you go rightward, the points increase. Okay, no matter at which level they lie, any point that lies to the right of any other point will be considered greater than that other point. So besides having these things increasing straight up, okay, let me just show the directions so that it becomes even more clear. On a single vertical line, this is how things increase. And along with that, this is the other direction in which things increase regardless of their level, at which level they lie. So that means exactly how is this order going entirely? You are starting at this point 1, 1 and things increase like this, and then you come to this point, and from there things increase like this, and anything which lies on this line is less than anything that lies on this line, which in turn is less than anything that lies on this line. So the order goes like this. Okay, first like this, then this, then this, then this, like that it goes. So now that we have a clear geometric idea of how the order is going, we can decide these things more easily. Let us now see which elements have immediate predecessors. Immediate predecessor means you take an element just before that element, whatever element you are going to encounter which is just less than that element is by definition its immediate predecessor. You will get many elements which have immediate predecessors. For example, if you take this element, its immediate predecessor is this. If you take this one, its immediate predecessor is this. The one before that. Okay. So like that, almost all elements here have immediate predecessors, but there is a special subset of elements which do not have immediate predecessors, and they are these base level elements. Let me enclose them within boxes. Why though? See, the thing here is that as you go down, as you come down along a vertical line, any given vertical line, you keep on getting immediate predecessors until you hit this bottom element. Then in search of an element which is less than this, where will you look? Obviously, you won't look on that side, you will look on this side. So, any element that lies to the left of this bottom element is by definition less than this. But you just want the one which is less than this and is the closest. Is there anything like that? No. All the elements that lie on this vertical line, the one next to its left, are less than this. But which one of them will you choose as the immediate predecessor of this? Anything you choose on this, anything, say you choose this one, there is another one which is higher than that and still it's less than this. You choose anything higher, there is still another higher one which is less than your chosen one and is still less than this. So, these special elements do not have immediate predecessors. Okay, so we have identified that fact. What else can we say? Does the set have a smallest element? Yes. This is the smallest element. The element where the order has started. Okay, so we can now answer number 1, part 1. And this will be our answer. That means from all the elements from this entire set, set plus times set plus, you have to remove those bottom elements, and those are the elements which have y coordinate equal to 1. That is why the set of elements which have, let me just write in short like this, okay, you will understand. Immediate predecessors is, let me call it S1. From the entire set, we remove those elements whose second coordinates are equal to 1. They form this Cartesian product. So these are precisely the elements, or this is precisely the set of those elements which have immediate predecessors. The element is the smallest element. Okay, so we have done part 1. Now next let's go to part 2. In part 2 the definition is a little more complicated. Here instead of simply talking about the coordinates, we have taken combinations of the coordinates. So let us first recall the definition and then we will again draw a diagram. This time this is the case if this is less than this or they are equal and y0 is less than y1. Okay, now what will happen geometrically? Let's try to see this. Again we draw those points. I have drawn them freehand, but we will understand. I mean, it's really not straight, it's not going straight, but still you will understand. So let us first actually see some points, then we will understand. The first First one I say because this is the corner. Let us first look at these points which have the same x and y coordinates, and let us also draw a kind of a line which helps us see them together. For these points, for this point for example, x naught is 1 and y naught is also 1. So the quantity x naught minus y naught for this point is 0. 1 minus 1 is 0. That's also the case with this point 2 times 2, and so are with the other points as well on this line. To identify this line, we can thus use this difference x naught minus y naught, which for all the points on this line are equal to 0. So let us identify this line by writing a 0 here. Now let us look at the other diagonal line that lies below it. Some of the points on it are these 2, 1. Yeah, it can become confusing. Okay, so let us go systematically. 3, 1, so this will be 3, 2. 3, 1, 4, 1, 4, 2, 4, 3. Then 5, 4. So if you join these points as well, you will then get another such line. Okay, and the line of course will continue. For these points, on the other hand, unlike these points, what is x naught minus y naught? 1. Constantly it's 1 for all these points. And similarly, let us also draw that other diagonal which lies above this one. You can in a sense call this the first diagonal line our middle diagonal, because above it you will continue to get diagonals, below it also you will continue to get diagonals. What about these points? 1 times 2, 2 times 3, 3 times 4 and so on. If I draw say another one, 4 times 5, and it will continue like that. In this case, however, for these points x naught minus y naught is minus 1. And you now a pattern is emerging. You can now tell without even looking at the points what that number will be for the line below this line. It will be 2. And the line that lies above this line will have number minus 2. And this won't really end. I mean, of course, in a sense, you may think, if you are looking like at these things like this, you may think that the space is shrinking. But the space, of course, is not shrinking, because these lines are not supposed to end here on this side. They will just continue to go without any end. Okay, so you will continue to have these lines stacked on top of each other, and you will also continue to have lines like that. Okay, so more lines with negative numbers, minus 2, minus 3, minus 4, and the ones with positive numbers 2, 3, 4, 5 and so on. Because this line has the number 0, so I just called it the middle diagonal line. Now let's come to the order. What is our definition? The definition of the order says that along each such line, you of course have these quantities same. For example, for 2 times 2 and 3 times 3, x naught minus y naught, x minus y, that quantity, they are both 0. So to decide which one is greater, you will look at their y coordinates. the one having higher y coordinate will be considered the greater element. So in this order, along any such line, this is the direction in which things increase, like that. Okay, for all such lines, this is how things increase. But what about points that lie on different such lines? That will be decided by which point has this quantity less and which point has that quantity greater. So that can be seen by looking at these numbers. The higher this number is, the greater that point will be. So somewhat counterintuitively, any point that lies on this line is less than any point that lies on this line, because minus 1 is less than 0. So here the order actually is coming from the top. Okay, the top points actually are the smaller points, and you see it's very confusing in fact. If you start your journey say here, although this is not where the journey starts, this is how things increase. But then if you have say exhausted points on this line, there are infinitely many points, but say you have exhausted points on this line, where will you look for even greater points below that line? And there the journey again starts from here. So here the order goes like this, like that it goes. Okay, and it reaches this line and then continues to go towards the right side like that. On each line, the journey actually starts at a point. There is a starting point, just like the dictionary order had a bottom point where the journey starts vertically upwards along those lines. Okay, somewhat similar. Okay. You can also try to think of it as a tilted version of the dictionary order. The dictionary order increases like this and like this. This one also increases like this and like this. Alright, now next comes the question of which points have immediate predecessors. Almost all points have immediate predecessors except the starting points of these lines, where along each line the journey starts. Why though? Let us consider this point for example. Now immediate predecessor means you are looking for that point which is just less than 1, 1. For that you have to look at points on this line, above this line. But again, just like dictionary order, you won't really find that point which is just less than this. Any point you choose here, whether this or this, there is a higher point which still is less than this. Okay, so this fails to have an immediate predecessor. The other points on this line do have immediate predecessors. Similarly, this one also does not have. This one doesn't have. This one doesn't have. And similarly, these points also don't have immediate predecessors. So for this second one, you have this boundary points, boundary in this diagram. These points are precisely the points which do not have immediate predecessors, others have. But you see, just a rotation, if I use this language, you understand what I am trying to say. If you just rotate the dictionary order by 45 degrees, smallest element vanishes. Why? Because now things really are not starting at this point. You can continue to look at higher and higher lines, getting smaller and smaller points. So in this order, the set z plus times z plus does not have a smallest element. The set, no need to write it again and again. You can write a formal solution itself. The set whose elements have immediate predecessors, or to put it more simply, the set S2 in this case in place of S1 is this. This time we have to rule out these points which previously also we ruled out, but these points as well. That means union this is the set of points which have immediate predecessors. There is no smallest element. So you can immediately see that the second set has a different order type than the first set, because the first set has a smallest element but the second one doesn't have. Now next we come to the third one. In the third one, the definition is this. If either, this time however we have sum of coordinates, not difference, or these are equal and that other condition is same, y not less than y1. Now what will be the diagram for this one? For this one, the diagram is another rotation of the dictionary order, but instead of this clockwise rotation, you have counterclockwise rotation. We will see why. Once we see 2 or 3 points, it will become clear. We first of all, of course, have 1, 1, then 2, 1, this is 1, 2, 1, 3, 2, 2, 3, 1, 3, 2, 3, 3, and this will be 2, 3. Okay, so we have to add the coordinates now. The sum of the coordinates of this point is 2. So let me simply write 2. The sum of the coordinates of this point as well as this point, both equal 3. So we can draw a line here. Okay, unlike those lines in dictionary order and that other order, this is a line segment, it's bounded. So to identify this line, I write the number 3. Similarly, you can join these 3 points where the sum of the coordinates is 4. 3 plus 1, 4, 2 plus 2, 4, 1 plus 3, 4, and you can continue to draw more and more lines like that. You can imagine that the next one will have the number 5. Already you can see 2 points having sum of coordinates equal to 5. So now what is happening? You can understand that along each such line segment, which point is greater, that is still decided by which one has higher y coordinate, or in other words, which one geometrically lies above that other point. For example, along, this is just a single point, so nothing to say about that. In this line, on this line, the point 2 times 1 or 2 comma 1 has lower y coordinate than the point 1 comma 2. So this one is higher. So the direction of increase is this. Similarly, here 4x plus y coordinates is 4 for all points on this line. So then we look at the y coordinates 1, 2, 3. So here the elements increase like this, and that's the same direction on each line. But on different lines, how do we decide which one is greater? Well, you look at these numbers, they will decide which one is greater. So when it comes to points on different lines, this is the direction in which elements increase. So in this order, this is how things increase. First it starts here, then this, then like this, then like this. So like that it will go. Okay, so that's the way this order moves. Okay. Now what about immediate predecessors? Actually here, this is the best possible order for finding immediate predecessors among these three. Nearly every element has immediate predecessor. Those infinite availability of points that we had in the previous two cases, at the bottom points or at the boundary points, which is why you were not able to find immediate predecessors for those special points in those two previous orders, is absent here. Any point you looked at, there actually are finitely many points less than that point. So obviously there will be an immediate predecessor. For example, even if you look at this point, which initially may seem like it will cause problem, it's not a problematic point. Its immediate predecessor is this, because this is how the order is going now. So after this point, the next higher one is this. So for this point, the previous lower one is this. So all the points have immediate predecessors except this one. That is the only point which has no immediate predecessor. And you can see that just like the dictionary order, here also this point is the smallest point. Okay. So for this third one, we already have started there. That set of those points which have immediate predecessors is this. We just have to remove this one point from the set of all points. The smallest point is 1 times 1 or 1 comma 1. Okay, and then we come to the question of the order types being all different. We have already noted that the order type in 1 is different from the order type in 2. Why? Because in 1 there is a smallest element and in 2 there is no smallest element. In this one we again have a smallest element. So the order type in 2 is different from the order types in both 1 and 3. But what about 1 and 3? Both of them have smallest elements. Still the order types are different. Why though? Because in 3, every element has finitely many elements less than 8. That is not the case in 1. There are some elements which do not have some elements means nearly every element, except those elements that lie on the first vertical line. Any other element has infinitely many elements less than 8. That is why these two order types are also different. So this is the entire idea of this solution. Now you have to write this rigorously and do understand that you cannot simply draw some figures and say, oh, that's why we got this. You have to justify everything. If you say in the dictionary order, if you take an arbitrary element, say this element which is not an element in this set, that means y is not equal to 1, you have to say precisely what its immediate predecessor is, because then only you can claim in the solution that this is the immediate predecessor, and also if that is somewhat doubtful, you show why it is the immediate predecessor. So you have to do all these things, okay. So I am leaving this to you. And the other exercises that we have in this section are also left to you as challenges. Otherwise, we cannot move forward if I keep on solving just about everything. So I primarily did this section because there is another section in this chapter which deals with something called a minimal uncountable well-ordered set, which is very important. It gives us a specific topological space. That's an important example. That is why I needed to do these sections. So once we complete that other section as well, we can then go to the proper topology, then it will start. Okay, and tomorrow we really do have class 11 mathematics actually, but I have decided to start class 12 tomorrow. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.